In the summer of 1908, Onnes summoned his chief assistant Flim from across the river. They were finally ready to liquefy helium. At 5:45 on the morning of July the 10th, he assembled his team at the lab. They had rehearsed the drill many times before. Leiden was a small university town, and the word quickly spread that this was the big day. It took until lunchtime to make sure the apparatus was purged of the last traces of air. By 3 in the afternoon, work was so intense that when his wife arrived with lunch, he asked her to feed him so he didn't have to stop. At 6:30 in the evening, the temperature began to drop below that of liquid hydrogen. But then, it seemed to stick.
Onnes doesn't know why this is. And a colleague comes in and he suggests that means maybe they've actually succeeded and they don't even know it yet. So Onnes takes an electric lamp type thing and he goes underneath the apparatus and looks, and sure enough, there in the vial is this liquid sitting there quietly. It's liquefied helium.
They had reached minus 268 degrees Celsius, just 5 degrees above absolute zero, and finally produced liquid helium. This monumental achievement eventually won Onnes the Nobel Prize. When James Dewar heard that he had lost the race to Kamerlingh Onnes, it reignited a festering resentment. Dewar berated his long-suffering assistant Lennox for failing to provide enough helium. Only this time, Lennox had had enough. He walked out of the Royal Institution, vowing never to return until Dewar was dead. And he kept his word. For Dewar, it was the end of his low-temperature research. James Dewar's dream of reaching absolute zero was over. Although he had won the first race to liquefy hydrogen, it never attracted the same accolades as liquefying helium. He abandoned low-temperature physics and moved on to investigate other phenomena, such as the science of soap bubbles.
I think it's really impressive how often scientists do seem to be driven by the spirit of competition, by the spirit of getting there first. But what's really fascinating about these races, the race for absolute zero, is that the goalposts move as you're playing the game. The race in science is not for a predetermined end, and once you're there, the story's over, the curtain comes down. That's not at all what it's like. Rather, it turns out you find things you didn't expect. Nature is cunning, as Einstein would have said, and she is constantly posing a new challenge, unanticipated by those people who start out on the race.
This is just what happened in Leiden, as Onnes's team began to investigate how materials conduct electricity at very low temperatures. They observed in a sample of mercury that at around 4 degrees above absolute zero, all resistance to the flow of electricity abruptly vanished. Onnes later invented a word to describe this new phenomenon. He called it superconductivity.
We have a circular ring of permanent magnets which are producing a magnetic field. And now when we put a superconducting puck over it and give it a little push, the magnetic field repels the superconductor.
The magnetic field from the track induces a current in the superconducting puck, which in turn creates an opposite magnetic field that makes the puck levitate.
It produces a magnetic field like a North Pole against the North Pole, and that's why you have the repulsion.
As the puck warms up, its superconducting properties vanish, along with its magnetically induced field. For decades after its discovery in 1911, the underlying cause of superconductivity remained a mystery.
Every major physicist, every major theoretical physicist had his own theory of superconductivity. Everybody tried to solve it, but it was unsuccessful.
There were more surprises ahead. In the 1930s, another strange phenomenon was observed at even lower temperatures. This rapidly evaporating liquid helium cools until at 2 degrees above absolute zero, a dramatic transformation takes place.
Suddenly, you see that the bubbling stops and that the surface of the liquid helium is completely still. The temperature is actually being lowered even further now, but nothing particularly is happening. Well, this is really one of the great phenomena in 20th century physics.
The liquid helium had turned into a superfluid, which displays some really odd properties.
Here I have a beaker with an unglazed ceramic bottom of ultrafine porosity.
Ordinarily, this container with tiny pores can hold liquid helium. But the moment the helium turns superfluid, it leaks through.
We call this kind of flow a superflow.
Superfluid helium can do things we might have believed impossible. It appears to defy gravity. A thin film can climb walls and escape its container. This is because a superfluid has zero viscosity. It can even produce a frictionless fountain, one that never stops flowing. Superfluidity and superconductivity were baffling concepts for scientists. New radical theories were needed to explain them. In the 1920s, quantum theory was emerging as the best hope of understanding these strange phenomena. Its central idea was that atoms do not always behave like individual particles. Sometimes they merge together and behave like waves. They can also be particles and waves at the same time. Even for great minds like Albert Einstein, this strange paradox was hard to accept. In 1925, a young Indian physicist, Satyendra Bose, sent Einstein a paper he'd been unable to publish. Bose had attempted to apply the mathematics of how light particles behave to whole atoms. Einstein realized the importance of this concept and did some further calculations. He predicted that on reaching extremely low temperatures, just a hair above absolute zero, it might be possible to produce a new state of matter that followed quantum rules. It would not be a solid or liquid or gas. It was given a name almost as strange as its properties: a Bose-Einstein condensate. For the next 70 years, people could only dream about making such a condensate, which has never been seen in nature.